This is problem 1359, it's on page 724. A mixture of hydrocarbon gases is composed of 60% methane, 25% propane, and 15% butane by weight. This mixture is compressed from 100 kilopascals and 20 degrees Celsius to 1,000 kilopascals in a reversible isothermal, in other words, constant temperature, steady flow compressor. Calculate the work and heat transfer for this compression per unit mass of the mixture. All right, well, let's make a sketch of what's going on here. We've got a compressor. Let's see, something like that. There's power flowing into this compressor, and this compressor then takes a mixture of gases from state 1 up to state 2. The mass fraction of the methane, I'm going to write that as CH4, is 0.6. I'm not going to use the subscript M here because M stands for mixture in this context usually. So I'll write CH4. But notice that it is these percentages by mass. And so if those are the percentages by mass, then what they've really done is simply given me the mass fractions. The mass fraction of the propane is 25%, and the mass fraction of the butane is 15%. So adding all that up, we got 40%, 60%, so yes, that's 100%. So there are the various mass fractions. The incoming pressure, so in other words, the pressure at state 1 was given to be 100 kilopascals, and the temperature at state 1 was given to be 20 degrees Celsius, which is the same thing as 293 Kelvin. The exiting pressure was given as 1,000 kilopascals, and they told us that this mixture is compressed isothermally. In other words, the temperature in state 2 equals the temperature in state 1. It's also reversible. So this is a reversible compressor. And what they wanted us to find, if this is the given, what they wanted us to find was the specific work input and the specific heat output, because there's heat loss during this process. All right, the first thing I want to do is get some properties of the mixture, but I'm not sure what properties I need. Why don't I just try to find out what it was they wanted me to find out. So the specific work in, well, to find that, what I need to do is find a reversible steady flow work equation for isothermal behavior, and that's all the way back in, I believe, chapter 7. Let me look at the summary. So we just need reversible steady flow work equations. And sure enough, page 397 has some for us. It says, now the three equations that are here in the left-hand lower section of the column are isentropic, polytropic, and isothermal. Now all of these are reversible equations. However, the one that is for isothermal is listed last, and it is as follows. It says that this work is RT, natural logarithm P2 over P1. So we know the temperature, we know the pressures, the only thing we don't know is the gas constant. So this really is not that bad of a problem. If we just knew the gas constant of this mixture, we'd be okay. Well, the apparent gas constant of the mixture is the universal gas constant divided by the molecular weight of the mixture, or the apparent molar mass of the mixture. The universal gas constant is no problem, I've got that memorized, but the average molecular weight needs to be calculated. So what I'm going to need is the molecular weight of each one of these things. So let's see, I guess I could write them down, or I could just write them in the context when I calculate it. If you look at the back of the chapter, you'll find this equation for the molecular weight, or the apparent molecular weight, of a mixture of gases when you have the mass fractions. All you have to do is take the mass fraction of the particular substance one at a time, divided by its molecular weight, add them all up, and you've got it. So in our case, we've got methane first, its mass fraction is 60%. And then you have to look up the molecular weight or the molar mass of methane, but it's 16, and I'll give you the units in just a second. They're all the same. They're kilojoules per kilomole. Excuse me, kilograms per kilomole. And then the next term for the propane is 25% by mass of propane. The molecular weight or the molar mass of the propane is 44.0, again, kilograms per kilomole. And then the last component is the butane. So 15% butane divided by the molecular weight of butane, which is 58, if I can read my own writing. Yes, it's 58, there we are. Now the units of all of these is kilogram per kilomole. We'll invert it once because they're in the denominator of the denominator, but we invert it again to bring it to the numerator. So overall, these will all be kilograms per kilomole. Let me just write down the result. It comes out to about 21.8493 kilograms per kilomole. So it's not surprising that it's somewhere between these, right? It's not surprising it's weighted closer to the 16 than to the other two because there's more of it. 60% of this is methane. So there's our molar mass, or our molecular weight of the mixture. So now that we've got that, we can calculate the gas constant, 8.314 kilojoules per kilomole per Kelvin, divided by the molecular mass of the mixture, 21.8493 kilogram per kilomole. Kilomoles go away, and we'll be left with the gas constant. It comes out to about 0.3805 kilojoule per kilogram per Kelvin. And so let's see, so the mass, I'm sorry, not the mass, the mixture apparent gas constant, 0.3805, can be used so that we can calculate the specific work input. Okay, so now we need the temperature. We're going to need it in absolute units, of course. Take care of Kelvin. And then we need the natural logarithm of the pressure ratio. It's easy to see that P2 being 1,000, P1 being 100, that ratio is 10 to 1. So I just need the natural log of 10. I'll go ahead and write the whole thing out, though. But I'm not going to put the pressure units in it. They cancel anyway. So what do we have left? Well, we have something that will be kilojoules per kilogram, which will represent the specific work. Plug in all of this into your calculator, you'll find that the number is 256.7 kilojoules per kilogram. So there's the specific work required. Now they also wanted to know the heat transfer rate out. We've got W in, now we need Q out. To do that, we're going to have to use an energy balance. So an energy balance would just say that the energy flow rate in this case, equals the energy flow rate out. Or power in equals power out, because this is just a system operating at steady state. Now what has power coming in? Well, the work does, and so does the mass flow. So on the left-hand side of the equation, what we'll have is the mass flow rate times the enthalpy in state 1 coming in, plus the power input in the form of work equals, what do we have leaving? Mass flow rate. The mass flow rate obviously at 1 and 2 is the same. Okay, it's obvious, it's single inlet, single exit, so I don't have to write a subscript 1 and 2 here. But anyway, enthalpy in state 2, that's what the exiting stream carries with it, plus Q dot out. Now I can write the power, the work power and the heat power as follows. M dot H1, I can factor out an M dot like that. Obviously that's power in, okay? So just factored out the mass flow rate from the work power. And then factor it out also from the heat transfer rate. There we go. And now the mass flow rate cancels and I don't need it. Okay. Now if I put the enthalpies together, well, let's see, something like this. H1 minus H2 plus work in equals Q out. Well, I can represent the change in enthalpy as Cp delta T, T1 minus T2. But wait a second, T1 minus T2 is 0 because the temperature in and out is the same. So the power, the work per unit mass that flows in is equal to the heat that flows out per unit mass. And so what that means is this is simply 256.7 kilojoules per kilogram. So there's our specific heat flow out, which finishes off the problem.